Hello, I'm Gellért Weisz, and I'm going to talk about exponential lower bounds for planning in MDPs with linearly realizable optimal action value functions. This is joint work with Amortila and Csaba Szepesvári. So we consider stochastic MDPs in the fixed H horizon setting. This construction that we will show also works for the discounted setting, but we will mainly talk about the fixed H horizon setting. In this setting, we define the optimal action value function Q star for each stage H, going from 1 to capital H, according to the Bellman equations in the usual way. And we define the value, optimal value of stage H plus 1 to be always identically 0, because that is the end of the episode. Other than this, we also define the value of a policy to be the expected sum of rewards that we gain by following some policy, and the expectation is over the trajectories generated by that policy. We make two assumptions. One is that the MDP has rewards supported on 0, 1. And then two, that the Q star function, the optimal action value function corresponding to the MDP, is linearly realizable. And what that means is that the planner, because we're going to be looking at planning, is given a feature, a d-dimensional vector for each state, action, and stage, such that there exists a d-dimensional hidden weight vector, such that the Q star at stage H of state and action is exactly equal to the inner product of that feature and the hidden weight vector. So the feature is known and the weight vector is unknown. In this sense, no matter how many states or actions the MDP might have, we only have d parameters, this theta star vector, to learn. We also set up this permissive setting of planning where we have a planner that has access to a generative model, a simulator. And so when the planner sees a state, it can go away and make some queries to a simulator before it returns with an action to perform. We also don't care about the computational cost. We only care about the number of queries made to the simulator. And any query of state and action to the simulator returns a possible transition of the MDP. And there will be capital N queries before the planner decides to return an action. Capital N is, in this case, a random variable. So if we use this planner by performing the action it tells us to perform, and then observing the next state and feeding that into the planner and closing the loop in this way, we are then executing a policy, pi, and this is called the planner's induced policy. What we want is that this policy should be close to optimal, and for that we define the suboptimality gap of any policy pi to be the value of the value that we lose out on by following the policy pi instead of following the optimal policy pi star, which would have value v star. And we also say that a planner is sound if for any Q star realizable bounded MDP, the planner's induced policy satisfies that this suboptimality gap is at most a constant. Our theorem says that any sound planner has worst case expected query complexity that is exponential in either the feature dimensionality d or the horizon capital H. So the worst case expected query complexity is really defined as the expected query complexity for the MDP that satisfies the assumptions and that maximizes this expectation. All right, so we show the lower bound by showing a construction that is showing an MDP that satisfies the assumptions for which there is no planner that can solve this MDP in a polynomial time. So this MDP is a tree. That means it will have deterministic transitions, and it will also have exponentially many actions. And always the same action A star is optimal, no matter where we are in this tree. There is also only up to one transition per episode that carries any reward. And this could be in one of two ways. either when A star is played, that is the optimal action is played, in which case the reward is about 2 to the minus h at stage h. So it decreases at a geometric rate for the stage we are in. And then if A star is played, we transition to a game over state, which means there will be no more rewards, and it doesn't matter what you do there. It will just go with 0 rewards to the end of the episode. Okay, the only other way in which there will be any reward is when we are in the last stage. Then no matter what action we pick, the reward is going to be a Bernoulli with expectation that will roughly scale with 2 to the minus capital H. So the same sort of geometric rate, but in this case, it's at the end of the episode, and this expectation is extremely tiny. There is another technicality, which is that if you repeat an action at any point, you get to a game over state and you don't actually observe any reward at all. This is just to discourage the planner to use the same action twice in an episode. So the outline of the proof is that the planner learns nothing unless it happens to pick A star, or if it observes a Bernoulli outcome of 1. But there are exponentially many actions, and if there are only polynomial queries, then the first of these will happen with a very low chance, but also the second of this, the Bernoulli, will also happen with a very low chance because its expectation will be so tiny. It will always happen to be 0 if you only have polynomially many queries. So this means that the wrong action will be picked at the root of this MDP with high probability, which will give us a constant suboptimality gap for this policy. So this is how the proof is going to look like. But let's talk about the features first. For this, we use the Johnsonlinostros Lemma. And what this lemma says is that there are exponentially many d-dimensional vectors, that is exponentially in D, such that any two of these vectors are almost orthogonal. So these are unit vectors such that any two different vectors will have an inner product whose absolute value is upper bounded by some small gamma. And in this case, for simplicity, let's say gamma is 1/4. We show an example here with a circle and 3 vectors that are almost orthogonal in a 2-dimensional space. The idea is that there's exponentially many of them, and each of these corresponds to the features of an action. Any one of them could correspond to the optimal action. So one of them will correspond to the optimal action, but the planner doesn't know which one, and it has to find out. So the features look like this. Well, first of all, the hidden weight vector theta star is a concatenation of the scalar 1 and the Johnson-Linus vector associated to this A star optimal action. And then at stage H, the features corresponding to a state S and action A will be a concatenation of a constant corresponding to the stage H and a scaled version of the Johnson-Linus feature for action A. So we have a shift of CH and a scale of sigma SA. The CH will be decreasing at a geometric rate, about 2 to the minus h. And then the sigma SA, the important bit about that is it must not depend on A star, because it must not reveal any information about the identity of A star. However, the sigma, that is the scaling constant corresponding to action A star, can depend on A star, because then it reveals no information about the identity of A star. So that is going to be an important insight into how we construct these shifts and scales. Okay, so we want to show realizability for this MDP and with the features that we talked about. And in the case when there are any rewards, when there is a reward in a transition, this holds by definition because there's only ever going to be one reward of that MDP, and that reward will by definition have an expectation that is exactly the inner product of the features and the weight vector. Only in the cases where there are no rewards do we need to prove anything. And for this, we first make an assumption. We assume that A star is always the optimal action, and we will come back to this later. But if this is the case, then what does the Bellman equation look like? Well, we no longer have a max operator because always A star is the optimal one. So what it looks like is that the Q star of S and A at stage H will have to equal the next state Q star for action A star. And so the next state we denote by SA because we have deterministic transitions. We can just denote it by SA. Okay, so if we plug in the definitions of these, as in the inner product, then what we see is that this black equation has to be satisfied, which means that that blue equation under it will have to be satisfied for A star. However, the sigma cannot depend on A star. So let's just make it true for any A prime. It doesn't matter if it's A star or not. For any A prime, we have the following definition of sigma. And then this means that this scaling constant will reveal no information about the identity of A star. However, the question that remains to be solved is, does this scaling satisfy the assumption that we made of A star always being optimal? And to see that, we propose that this scaling constant will always have values between gamma and 1. And if this is the case, then we're sort of done, because we know that there is a gamma factor difference between the inner products of two different vectors and the same vector, the optimal vector. And this is the case because the Johnsonlinostros Lemma says that any two different vectors will have an inner product that is at most gamma in its absolute value. And so because there is this gamma factor difference, at least, therefore, by scaling things up to a gamma factor, will not actually change a suboptimal action into being an optimal action, or an optimal action to being a suboptimal action. So this means that the red star assumption of A star always being optimal is satisfied. And so what we need to show is now this blue star assumption of the scaling constant being between values gamma and 1. And so for this, we kind of show how the shift and scale works together to control this. And so in this case, in the first stage, we have a C1 constant plus the inner product that we could see. If we pick action A star, then we see the maximal inner product, and then we observe this constant reward. However, if we pick any other action, then this inner product, because of the Johnsonlinostros Lemma, will be a gamma factor lower. So it will correspond to this blue range of possible Q stars. And so what we need for realizability is that in the next stage, when you have C2 as the shift, this red arrow will be the range of scaling, right? Because depending on what action you picked and where its Q star lied, you have to scale the next state's features such that the A star optimal action will get you the same Q star. And so this range of scaling, this red, is controlled by carefully choosing the constants C. And in this case, this blue star equation inequality will be satisfied. And then we have realizability. So to recap this proof, for the planner to solve the MDP, the action A star has to be found. And this can be done in one of two ways. Either the planner has to randomly stumble across this action out of exponentially many actions, or it has to see a Bernoulli taking a value of 1. So the former corresponds to an exponential sample complexity, at least in D, and the latter corresponds to an exponential sample complexity, at least in H. This same construction can also be applied to the discounted setting as long as your discount factor is at least 2/3. And the only difference is that you don't now have a final layer. So the second case goes away and you have an exponential in D query complexity lower bound. We also have an upper bound which works only in the fixed horizon case. And this is essentially doing least squares value iteration with G optimal design. So it uses bootstrapping. It sets the approximate values for stage H plus 1 to be identically 0. This is true by definition. And then it will go from stage H, that is the final stage, down to the first stage. And at each stage, it will compute a near G optimal experimental design on the features that are available in stage H. This will give us a distribution of polynomial support and this can be computed in polynomial time. And then what we do is we measure Q star accurately as we can on this support using bootstrapping, using the values of the next stage, the approximate values that we computed in the previous iteration. And then, after knowing the values on the support, we extend that to the values of all the states and actions in this stage by calculating the weighted least squares estimate. And then we go on and go down to the first stage. And so the inaccuracy that we will have will accumulate at an exponential rate in h. So the query complexity that we can have with this algorithm is scaling in this manner as an exponential in capital H. So if you want a polynomial out of this, then the delta, which is your inaccuracy, will have to scale exponentially in H as well. So to sum up, what we answer in this paper is this question of, does linear realizability of Q star and a generative model allow us to scale to MDPs with many states and many actions, that is exponential states and exponential actions? The hope would have been that yes, this would be possible because you only need to learn D parameters. But the answer is that no, this isn't actually true. Linear realizability isn't enough to scale to exponentially many actions. However, what remains an open problem is that if you have many states, that is exponentially many states, but only polynomial in D many actions, then does linear realizability of Q star help you come up with a polynomial sample or query complexity planner? This is still an open problem. Finally, in subsequent work, we explore this question with V star realizability instead of Q star realizability. Perhaps surprisingly, we find that with a small order 1 number of actions, there is a sound planner with a query complexity that is polynomial in all the relevant parameters. This leaves open the question of whether this is possible with a polynomial in D number of actions. Thank you.